Hello there. We're going to continue our adventures with Onyx, this time considering a two-predictor regression model. And in order to build on our skill set, we're going to do a few new things in Onyx that we didn't do last time, such as giving specific names to the parameters in our structural model, reading in summary statistics rather than the raw data, and comparing models. So let's get started. So here we have Onyx, and we're now going to read in our data set. This will be the Wiedemann smoking example in the third chapter, looking at three variables. We see we have three manifest variables here instead of just two. And if we mouse over these, we will see that we have means and variances here. We don't see the full range of the proportions of individuals present and the percentile points here, because the raw data that are being read in are the summary statistics and not the entire raw data set. Let's take a little bit of a look at the summary statistics that Onyx needs in order to run a model based on these. Here we see it. Here's the format. Observed variables, all uppercase, new line, the names of your variables. This is separated by tabs. The word covariance and your variance covariance matrix follows. This is a symmetric matrix. What sits on the diagonal here are the variances of our manifest variables, and on the off diagonals we have the covariances. Following that, the word mean and the means of our manifest variables, and sample size and the sample size for the data. So when you're reading in summary statistics, you're assuming there's no missing data going on here. It would be nice. Some things like Amos will let you read in correlation matrices and standard deviations, but Onyx does not have that capability right now. So let's come back up here and create a new empty model and move that over. And the data set that we're looking at here has one dependent variable of the amount that these boys reported smoking cigarettes in the last 30 days. And we have two predictor variables here. Left click and right click and dragging those over. I've got my two predictors here. I'm going to space those out a little bit so I have some room here. And when I have two predictors, or any number of predictors in a multiple regression model, I'm going to join these predictor variables by means of a sling. So shift, right click, and letting up on that gives me a double-headed arrow indicating the sling, and selecting that, left clicking, and then freeing that parameter estimate gives me a covariance between those two variables. Let's look at that a little bit. Onyx defaults to giving you a name for that parameter that's a bit long. Sometimes that gets a little bit cumbersome in your diagram if you're going to be publishing it, or just for you to keep track of it. So you might type in some other name for it, such as cov, since it's the only covariance in the model. Similarly, last time I talked about the fact that you can apply a z-transform to these predictor variables and calculate a correlation. It is also possible to show the standardized estimate on that path by clicking the Show Standardized Estimates button. And that then shows us that the correlation between these two variables is 0.57. If I want to specify this as a regression model, I will now right-click and connect that to my criterion, and right-click and connect that to my criterion as well. And I can then select both of these models at once rather than just one, and then select free the parameter on that, and I can select show the standardized estimate. And as before, I can come in and give these some shorter names. I might want to just call this B1 and B2, for example. Now, these parameters are not completely lined up, and if you're thinking about neatness counting, you can left click on that and move it down so that it aligns with the other parameter estimate. Similarly, if you wanted to, up here on the variances for these variables, you could say, I want to also show the standardized estimate for these variances. Just to remind yourself that those standardized estimates and the correlation apply to the z-transform of those variables. Downstairs here, we can also put the standardized estimate for the error term of 0.79. That has a fancy name. That's going to be called the coefficient of non-determination. You may have also heard of it as 1 minus r squared. It's 1 minus the squared multiple correlation for your model. That 0.79 represents the proportion of variation in the criterion not explained by the predictor variables in your model. Second fancy thing to do now is to come in and take a look at the solution in table form for your parameter estimates. To see those, I can right-click, come downstairs here, and select Show Estimate Summary. This will give you an output of the particular parameters that you have. Because I have read in summary statistics, I'm not going to see the descriptive statistics on my variables here. Downstairs, I have my parameter names here, and I have various fit statistics that show the fit of the model. Now down here, you may have noticed that it's doing something in the background. Ωnyx is solving and solving and solving your problem over and over again. What you see up here are the unstandardized estimates for the various parameters of your model. It doesn't show you the standardized estimates and those standard errors. If you want those, well, you can get them out of the diagram, or you can get those readily by porting this particular problem to M+ or to Levant. You can, if you would like, save that script as a text file. Okay, that takes care of doing our regression model without an intercept. That is, our analysis here is based on the deviation score matrix, that is, the mean-centered model in the data. Sometimes we might be interested in putting the mean in the model, that is, estimating our regression model such that I get an intercept and unstandardized regression weights here. So to do that, I'm going to make this diagram just a little bit larger and move this down, because whenever I want to put the mean in the model, I'm going to have to add in that triangle, the column of ones. And what I will do here now is to put a path to the predictor variables. Select those both and free those parameters. And join the column of ones to the dependent variable and free that parameter. Perhaps I would like to come in and give that a name. This is going to be the mean of the insecure variable. And this other one is going to be the mean of the trying hard to look cool variable. As before, I can come downstairs here and move those down so I can be able to see those a bit more down here. And down here, I can give this the name V0, which is sometimes the term used to describe the regression intercept. So that basically is all there is to showing a regression model with an intercept, showing our values for the unstandardized and standardized estimates in that model. Sometimes it's of interest to know if one of these unstandardized regression weights is the same as the other unstandardized regression weight, or is something different. So to do that, we're going to have to compare these two models. This model in which they are different, and another model in which they are constrained to be the same. So let's give this model a name. We'll call it regression. Okay, so what we'll do is we'll save this work by right-clicking, going to File, and saying Save Model, and giving this to a name. We can call it regression, and that will save our Ωnyx model. Similarly, I can come in and then save this model as another one. I can then load this particular model in the data and bring it up over here. We can give this model a name, call it equal. And in order for us to constrain these two regression weights to be the same, we will simply give them the same name. Okay? This now is going to fit the model as we have. If we'd like, we can come downstairs and similarly show the standardized estimates for that model. We can see that it doesn't explain as much variance as the model in which these regression weights are allowed to be different. And if we wanted, we can also look at our standardized estimates that result from that equality model. And we can see that they're negative and slightly lower. The reason those standardized estimates look just a little bit different is the estimated variances of these two variables are different. And as a result, the standardized coefficients are going to look a little bit different as well. Now, to compare these models, I'm going to come over to one of the diagrams, hold down the right shift button and move over to the other one, and you'll now see that there's a little black dot that appears. I'm going to wait for a little bit until that model looks like it's stabilized. Sometimes I found that it's helpful to send the data to your two models, and that seems to help this stage over here of getting to see a model comparison work run a little faster. So now if I mouse over this little black dot, I will see a 1 degree of freedom log likelihood ratio test of 6,241, which is significant at the OOG's level, indicating that the hypothesis that these two unstandardized regression weights are exactly the same is very unlikely. Okay, that takes care of what I have for this objective in looking at two predictor regression models without and with the intercept in the model, and how to compare those two models. Thank you very much for your time.